Hello everyone, welcome to my class. In today's class, I'm going to cover arc length in space and the curvature. So let me start the class right away. So first, our goal in this section is to find a numerical value that measures the length between 2 points along the curve and the bendingness of the space curve. Next, definitions. Arc length. The arc length of a smooth curve given by the vector equations r t equals to the vector whose components are ft, gt, ht, or xt, yt, zt from t equals to a to t equals to b is denoted and defined by L equals to the definite integrals from a to b of the magnitude of r prime t dt. This equals to definite integrals a to b under the radical f prime square plus g prime square plus h prime square dt, or definite integrals from a to b under the radical x prime t square plus y prime t square plus z prime t square dt. Make sure the curve traverses exactly once, that is, it does not double back itself. Next, quick aside, if a curve resides only in xy plane and is defined by y equals to fx, then its corresponding vector equation is rt equals to the vector whose components are t, x equals to t, then y equals to ft, and z equals to 0. And in this case, the arc length between x equals to a to b turns out to be L equals to definite integrals from a to b under the radical 1 plus f prime x outside square dx. Next definition, arc length functions. Suppose s is the distance along the curve from some fixed point a, then we can define the arc length as a function of parameter t. So by st equals to definite integrals a to t absolute value of r prime u du. I already use t as our upper limit, so I put u variables here. Then by fundamental theorem of calculus, the derivative of s with respect to t is simply r prime magnitude. Awesome. Now let's move on. Quick remark. Remark 1. In the parametric curve, there are two ways to locate the position of a moving object. One in terms of time, and second in terms of the distance. 2. One application of arc length is the arc length parameterization of the curve. Note that a curve can be parameterized in infinitely many ways. Next, let's talk about parameterization of the space curve. If a curve is given in terms of t and s is the arc length functions defined as above, then solve for t as a function of s, such as t equals to function of s, such as t equals to function of s. Finally, substitute this back into the given curve rt to get rs. This process is called the parameterization of the curve by the arc length. Remark 3. The arc length parameterizations has unit speed. So always the magnitude of r prime s turns out to be 1. Remark 4. We would like to measure a curve at various points. How sharply the curve is bending. In other words, we would like to know how fast a unit tangent vector to the curve is changing the directions. We name this the curvature. Next definitions, curvature. The formula, we use kappa. Kappa equals to the magnitude of t prime s. In terms of general parameter t, curvature turns out to be the ratio of the magnitude of t prime over magnitude of r prime. Sometimes the following equivalent formula is simpler to compute the curvature. Kappa equals to the ratio of magnitude of r prime cross r double prime over magnitude of r prime cubed. I hope this makes sense to you all. Quick aside, if a curve resides only in xy plane is defined by y equals to a function of x, then its curvature turns out to be kappa equals to the ratio of the magnitude of f double prime x over 1 plus f prime x square outside power 3/2. Great. Let's move on. Quick fact, the curvature of a circle is constant and is reciprocal of the radius. Let's see a quick proof here. Consider a circle of radius a in xy plane given by rt equals to the vector with component a cosine t comma a sine t. Then find the r prime t. Then use the derivatives r prime. Then find its magnitude. The magnitude of r prime equals to a. So the unit tangent vector t equals to r prime over magnitude of r prime, which turns out to be the vector negative sine t comma cosine t. Then take the derivatives of unit tangent vector. T prime is the vector with component negative cosine t comma negative sine t. Then find its magnitude. So magnitude of derivative of unit tangent vector is 1. Thus, by formula, curvature kappa equals to the ratio of t prime over r prime magnitude. It turns out to be 1 over a constant. In fact, a small circle has large curvature and large circle has small curvature. Let me visualize here. Quick visualize. There are 3 circles. There is a small circle, then bigger, then the biggest. So if you pay attention on the tangent line here, the circle is in a smaller circle. The tangent line changes the directions quicker than the second circle and then the third circle. So that means in the biggest circle, in the third diagram, the unit tangent vector changes the direction slowly than the previous 2 circles. I hope this makes sense to you all. Let's move on. Facts. The curvature at a point of a curve describes the circle that best approximates the curve at that point. The curvature of straight line is 0. Next definitions. The TNB-Frame. T, the vector t, is the unit tangent vector. Indicates the direction of the particle on the curve. N vector, the principal unit normal vector, points to the inside of the curve in the direction of the particle is turning. B vector, the binormal vector, points directly upward and we don't care that B directions. So formula, unit tangent vector we already defined, which is the ratio of r prime over magnitude of r prime. Then normal vector, which is the ratio of the derivative of unit tangent vector over magnitude of derivative of unit tangent vector. And binormal vector is simply the unit tangent vector cross with unit normal vector. In terms of arc length, kappa is related to unit tangent vector and unit normal vector by these equations, and vector equals to 1 over curvature dt over ds. Awesome. So quick summary here. Let me explain this diagram here. This is space curve here. So the vector here is the unit tangent vector. This is the principal unit normal vector and this is the binormal vector. So always t points the direction of the flow and points the directions inside of the flow, where the flow is turning into, and B directions, we don't care, this direction points outward, and this TNB-frames rotates as the flow flows forward. So that means here this is a T vector, here is the N vector. So now here the T is this directions and N is this direction. The flow is turning into N directions and go here. Now this is my T directions and this is the N direction. So if you pay attention on this diagram, there is a circular motions there. So that TNB-frames always rotates in a circle. I hope this makes sense to you all. So now with this theory concept, now let's do some example. Worked examples. Example 1. Consider the helix given by the equations RT equals to the vector with component 3 cosine t, 3 sine t, 4t. Answer the bunch of sub-questions from A through E. So part A. Find the length of one coil of the helix. That means T between 0 to 2 pi. So solutions, let's apply the formula. So the formula is L equals to A to B, the magnitude of R prime t. So let's first find the R prime t and its magnitude. So find the derivatives of RT. So then 3 cosine t becomes minus 3 sine t. 3 sine t becomes 3 cosine t, and 4t becomes simply 4. Find the magnitude of R prime, which gives us 5. Hence by formula, arc length equals to the definite integrals from 0 to 2 pi of 5 dt. So the answer is 5 times 2 pi is 10 pi. I hope this makes sense to you all. Let's move on. Part B. Find the arc length parameterizations of the helix for t between 0 to 2 pi. So now first we need to define the arc length functions, and then we need to find out Rs. First, let's find the arc length functions. S equals to, by definitions, definite integral 0 to t magnitude of R prime u du. We already computed the magnitude of R prime, which is 5. So then this equals to, in the next step, a definite integral 0 to t 5 du. This equals to simply 5t. So then solve for t. So t equals to s over 5. And finally substitute this value back in RT. So put t equals to s over 5 in the given equation of the curve. Hence we get Rs equals to the equation of the curve in S parameter. So the vector with components here 3 cosine s over 5 comma 3 sine s over 5 comma 4 s over 5, and s between 0 to 10 pi, t between 0 to 2 pi. So t is 0 to 2 pi. When t is 0, s is 0. When t is 2 pi, s equals to 10 pi. I hope this makes sense to you. And by the way, note both of these representations, one in terms of parameter t, one in terms of arc length s, these representation of the curve are the same curve. I hope this makes sense to you all. Now let's move on. Next, let's find in part C, let's find the magnitude of the derivative of r with respect to s. I mentioned earlier, this always turns out to be 1. And let's verify. So the derivative of 3 cosine s over 5 is 3 constant as it is. Derivative of cosine gives you minus, so this minus, sine s over 5, and by chain rule 1 over 5, so which is here. And the derivative of 3 sine s over 5 is 3 over 5 cosine s over 5, and the derivative of 4 times s over 5 is simply 4 over 5. To find the magnitude, so under the radical, first component is square plus second component is square plus third component is square, and you simplify, it turns out to be 1. Awesome. Let's move on. Part D. Find the curvature for the helix. So let's use the formula. The curvature equals to the ratio of the magnitude of t prime over magnitude of r prime. So first let's find the unit tangent vector t. So begin the solutions. Given curve is r equals to 3 cosine t, 3 sine t, 4t. Find the derivative of r. Find the derivative of r, which is r prime t equals to derivative of 3 cosine t is minus 3 sine t. Derivative of 3 sine t is 3 cosine t, and derivative of 4t is simply 4. Find the magnitude of r prime, which turned out to be 5. So the unit tangent vector t equals to, by definitions, the ratio of r prime over magnitude of r prime, which is just divide the r prime by 5, then 1/5, negative 3 sine t, comma 3 cosine t, comma 4. And next, find the derivative of unit tangent vector t and find its magnitude, which turns out to be the magnitude of t prime equals to 3/5. Hence, by formula of curvature, curvature equals to the ratio of magnitude of t prime over magnitude of r prime. So 3/5 over 5, it turns out to be 3 over 25. I hope this computation makes sense to you all. Now let's move on. Questions part A. Find T, N, B, and curvature. So T is a tangent vector, that's the unit tangent vector, and unit normal vectors and unit binormal vectors for the helix. Solutions, we already found the unit tangent vector and curvature. We found the curvature here and we found the unit tangent vector here. So let's find out vector N and vector B. So by formula, unit normal vector is the ratio of the derivative of unit tangent vector over magnitude of derivative of unit tangent vector. So it turns out to be, here's negative cosine t, comma negative sine t, comma 0. Great. Now finally, to find the binormal vector, let's cross the t vector with n vector. Then we know how to compute the cross product. Expand the determinant, 3 by 3 determinant. So the first row is I, j, and k. Second row is the component of unit tangent vector, and then the third rows are the component of unit normal vector. And we expand the determinant. Then this gives us 1/5. The vector negative 4 sine t, comma negative 4 cosine t, comma 3. I hope this computation makes sense to you all. Now quick visualizations. This is the helix, and at some point here, this is the tangent vector and this is the normal vector. The normal vector is pointing to the directrix, the z-axis of this helix. Great. Now let's move on. Example 2, find the curvature for the curve. The curve equation is given by RT equals to t, comma t square, comma e to the t, or ti plus t square j plus etk. Awesome. Now let's move on. So by formula, our curvature equals to, let's use this formula, the ratio of magnitude of r prime cross r double prime over magnitude of r prime cubed. So let's take the derivatives of RT, first derivative and second derivative, and cross them and find the magnitude of r prime and use this formula. So here r prime equals to, so only I plus 2tj plus etk, which is same as 1 comma 2t comma et. Then find the second derivatives. Then r double prime is, this 1 is 0, so 0, 2t becomes 2, et is et. So we have r double prime is the vector 0 comma 2 comma et, and Next, let's compute the cross product of r prime and r double prime, which turned out to be this vector, the vector with component 2et times t minus 1 comma minus et comma 2. Please make sure you got it. Next, let's find the magnitude of r prime t. So magnitude of r prime t is here. So under the radical, 1 is square plus 2t square plus et square. Next, find the magnitude of r prime t cross r double prime t, which is here, which is under the radical 2et times t minus 1, everything outside is square, plus minus et outside is square, plus 2 square 4, and simplify, it gives us this expression. Hence, the curvatures by formula, this numbers over this numbers, power cubed. So I hope this computation makes sense to you all. So we finish these sections. Thank you.